from now on, the program is gonna get a little bit more technical, and to start the trend, we have our own Brandy, who is a software engineer here at Facebook, working in our site integrity team, which is our anti-everything that is bad kind of team. It's a good way to put it, right? So with that, I'll leave it with him.
All right. Thank you. So, standard speaker pre-apology. I'm keeping you from lunch at this point, so I promise not to go over. As she said, so my name is Brandy. That's me. I work on the site integrity team, which she didn't say anti-spam, which is actually really good because spam is like a huge part of what we do. It's actually the dominant thing that we do, but obviously spam, the difference between like where security ends and spam begins is pretty gray, and so a lot of what we do spans this whole sort of universe. The reason I call out spam in particular, though, is it's sort of what gives you the scale. Dealing with spam at scale is a much more difficult scaling problem often than dealing with other kinds of things because you end up having the whole surface of the whole product, and every connection between every user ends up being a possible vector for spam. All right, so let's get started. So here's my background really briefly. I've spent the last 4 years basically building our anti-spam and anti-abuse infrastructure. So that's what I've done. You know, Facebook launches a lot of things. There's a lot of products happening all the time. One of the things we wanted to do is sort of make this system generalizable and easy for like to plug into the next thing that we ship. And this was a big important thing so we can ship things quickly, and if they take off, we can get anti-abuse into them as quickly as possible. This is like really important for like actually moving fast and actually getting things done and not having horrifying spam problems paralyzing things. We got a like supremely incredible test of this generalizability when one day Instagram shows up and we're like, okay, we've been training for this our whole lives. Let's see if this actually works. Let's see, like it's like meeting an alien life form. Like you don't know exactly what this is going to be, and let's see if the tentacles line up. It turned out, by the way, great. So like essentially now our systems, without too much effort, essentially classify and deal with spam and abuse on all of Facebook and Instagram, right? My team and the work that we do is very systems focused, so this is going to be a very systems-y talk, so there's not going to be anything spam specific here. That's somewhat intentional. I'm going to try to talk more about the scaling part of what we do, and hopefully it's more applicable than just to what might happen in spam. So where I started with all this is like if I was going to pick the thing that's the most important and obviously generalizable, right, that's not domain specific, where would I start? And the answer to this question actually comes from a surprising place, right? So we're at a Security at Scale conference. There's like a security and spam domain. There's a scaling world of distributed systems and all these other things. And the bulk of my talk is neither of those. So here's our agenda. I want to take you on this journey. I want to start with our systems at the highest level. I want to show you a really abstract, very quick sort of overview of everything that we have. I want to sort of laser in on the largest system, the one that causes us the most problems. And I want to isolate for you the actual scaling challenges that we've overcome. It's at about this point, things are going to get a little crazy. I'm going to throw a blindfold on all of you. I'm going to spin you around till you're sufficiently disoriented, and we're going to throw you in the back of a van, and you're going to wake up in the heart of functional programming by the end of this talk. Yes, great. So this is going to be a cross-functional talk. I'm warning you ahead of time. The word monad is going to appear in this talk. Yes, all right. How many functional programmers? Oh, excellent, great. So for the rest of you, that's okay. Don't be afraid, except for the van ride. That part will be sketchy. But otherwise, this will go fine. All right, so we start at the beginning, okay? Everything, right? First, create the universe, right? So if I was going to sort of tell you what to build, if you were going to fight spam and everything else on Facebook, you're going to have to start with manual investigation, right? You need to know what's happening on the site. You need to be able to find bad things, okay? That's like a pretty standard place to start. This isn't super generalizable. I can't give you good advice here necessarily, though there are probably talks that live in this world. Once the humans have established patterns, then you need computers to enforce those patterns. That's like you want to teach computers tomorrow what you're doing repetitively today. That's sort of the iteration cycle that we're going through. And then whether the humans or the computers detect something squirrely has happened, right, an anomaly of some sort, you need to be able to remediate. And remediation seems easy at first, like just block it, just erase it, just launch the missiles, right? Whatever you need to do. It actually can get really hard, and you can actually have entire teams devoted to, in fact, companies, right? Antivirus software is like a form of remediation, right? We're going to focus today on number 2, right? So this is where the computers are doing most of the work, and that's because that's where the scaling comes from, and that seems like a good topic for today. So I want to talk about teaching computers to find evil things. So here is my hopelessly abstract architecture diagram. In fact, it's so abstract you can't disagree with me, right? All systems will fit this particular model. So in the beginning, you have an event, okay? A user wants to post a photo to Facebook, right? Somebody wants to log into the email server, okay? Somebody wants to get a job at the FBI, okay? An event. All I have to do is teach a computer to determine, is this event evil, right? Easy. So if you can do this, come find me, you're hired, right? And if it's evil, go see step 3, remediation. But if it's not evil, commit it, okay? So database is my icon here. Store it to the database, give them a job, right? Whatever the event is that actually makes this occur. So this is like really simple, okay? This is not rocket science or anything. But a really important design decision has already been made, right, in our system here. And that is that my evil check is synchronous, right? So it can't happen until I say it can happen. And so that's great for like the anti-abuse team, but like somebody's gonna notice eventually that like a login takes 45 seconds, right? Why does login take 45 seconds? Like, you don't understand, it's the greatest neural network that's ever been trained, right? But so you have a natural tension at this point. And so what you end up doing is you put all your fast checks at the beginning, and you'll do some asynchronous checks after the fact, right? And so you'll dump something to some log, again, metaphorically, obviously a literal log often, but not always a literal log, some form of thing that you can review what's happened. And you can basically run the same checks later. Now, you have the advantage here, right, that you're not time sensitive here because it's already happened. It's not really impacting your product experience for whatever the definition of that is. But the downside is it's happened. So if it's evil, it has some window to do harm. And sometimes you can't even undo it, right? If what you're protecting here is somebody seeing something they shouldn't see, the cat is out of the bag, right, so to speak. There's still another weakness in this architecture, which is like it has no memory, right? Per event classification is great, but you'll eventually hit walls where you can't do much. So you start to aggregate, cluster. Show me all the events associated with such an IP address. Show me all the events associated with, this email domain, this URL, right? Things like that. And then you can start to classify clusters. And this gets really, really powerful, right? You can start to, keep track of reputations of different kinds of aggregations. You can start to build really high recall, high precision classifiers. So the moral of all of this story, and basically this is what Facebook's architecture looks like. We have all 3 of these, and we use all of them extensively. But at the heart of all 3 of these is like a rule engine, okay? That's where I'm headed today. That's what I want to talk about. By the way, I did not plant the previous speaker, right? Like Sting, right? Is that what it's called? Panopticon. Those are rule engines, right? Like they're in there, right? There's a rule engine. Basically, how do I detect something crazy and how do I fire off some response? And what is that business logic? I mean, he even had a flow chart, right? That's perfect. Perfect lead in. Oh, by the way, oh no, I've jumped ahead. So I said all this. Yeah, so the interesting bit is this rule engine here at the beginning is actually the most important because it's synchronous. The other ones are not. That means it's latency sensitive, okay? That means you cannot put expensive checks there. But it is the best place to stop abuse, right? By far the best place to stop abuse. So you have a tension, right? The anti-abuse wants everything here, and all the product people kind of want to pull it this way. There's actually an infra reason to do this too, because if you allow evil stuff here, and then you have to clean it up later, you are like write amplifying the bad guys, right? They get 2 writes to your database, right? Once to put it in and once to take it out. And that will make your infra teams very upset too when the databases start falling over. So onward, okay, this is what I jumped ahead. As an aside, this is a really interesting problem. Like clustering and keeping track of reputations at scale across all the different things you might aggregate at Facebook is in and of itself an excellent talk of this kind, but it's not today's talk. Maybe next time, 2015. So this is where I've headed, right? Latency sensitive rule engines. This is what I want to talk about today. What is a rule engine, right? You pass in some data, you smash that data together and return responses depending on whether your rule, your business logic, right? If something shady happened, launch the missiles, right? Whatever you need to do. At their heart, like the beginning of every rule engine is what is known as pure functions. So the functional programming, you see it coming, right? You can see it coming from here. Pure functions, for those of you that forgot that class, right? Anything that depends only on its input and has no side effects, okay? So add, subtract, multiply, match a regular expression. These are all things that are just functions of their input, right? They're not fetching data. There's no global state or anything like that happening. No writes happening to the outside world. So a problem very quickly arises in your rule engine that's based entirely on pure functions is like the next rule that you want to write, you don't actually have the data that you want. You need to add a field. You need to add a dimension. And so you can do that, right? You can like build the system and like every time you need something, add it to be fetched ahead of time, pass it into your rule engine, make more decisions. And what ends up happening, of course, over time is you're prefetching everything that you might ever need, which is a horrible latency hit. And most of the time, you won't need most of the data, right? Most of the time, you don't need most of the data, right? So what you really want is supplementary data fetching in a rule engine. This ends up being an amazingly sweet space in the design space. Basically, what you want to say is if the input looks shady for some simple definition, then let's do all the expensive stuff. Let's go fetch all the data in the universe. Let's make a classification, right? So you want supplementary, often conditional or lazy data fetching, okay? When we speak from a latency perspective, the moment I hit the network, like the moment I'm going to read a database, there is only one thing that exists as far as latency is concerned, right? So all that's free. All that matters is fetching data. That's what ends up happening in my latency-sensitive rule engine, right? So has everyone bought in so far? Okay, I saw one nod, so that means everybody. So I will make the controversial statement that Facebook employees can argue with me. So one of the most important things that we've built is our scalable latency-sensitive rule engine, okay? We built it to have a really expressive rule language, right? I don't want notions of efficiency in my business logic at all. I want really simple business logic. And what I want is that logic to be implemented in such a way that all the data fetching that happens under the hood is super, super optimized, okay? This has been wildly successful at Facebook. Like betting heavily on this system has been incredibly successful, right? It handles every single write request to Facebook and Instagram synchronously, okay? You can't do anything until this system tells you that you can do it. And more importantly, it's grown in the other dimension, which is lots of people use it for things that we didn't really expect because you have this incredibly powerful thing that can do things right there for you synchronously, right? So we have hundreds of thousands of lines of rule engine code running in this thing over all these surfaces, right? So that gives you a sense of the scale of the problem that we're trying to solve. So there's one assumption it's a reasonable assumption, but from the functional programmer's perspective, it makes your life insanely easier. And that is that your rule engine can't do observable writes during the request. Rule number 1 can't write some data that rule number 7 expects to see, okay? The moment I pull that out, and every programming language in the world sort of assumes that can happen, that you have this sort of top-down flow to your code. The moment I pull that out, everything simplifies, and a lot of magic actually happens. And this is not theoretical magic. I'll try to make it practical in a second. Data fetching becomes pure enough, okay? So the functional programmers are probably angry right now because it's not exactly true, but for the duration of a request, it's a totally safe assumption that if I fetch the friends of me in rule 1 and I fetch the friends of me later in rule 7, then I'm gonna get the same answer, right? And that makes data fetching pure with appropriate scare quotes, at least within a particular request. Pure functions are awesome. We're gonna abuse them in a minute. And as I mentioned this before, this actually simplifies the problem immensely, and it actually makes it possible to do things you simply can't do otherwise. So that's where I'm headed. So anyway, here's like as you sort of like take that axiomatically and you work out the mathematical consequences, a bunch of things really start to come together, right? So without any intervening writes, I can start to make assumptions. It means I can deduplicate any fetches in my rule engine, right? That's a big win already, okay? It means I can overlap independent fetches. So if I have 27 rules and they're all totally independent, they don't depend on each other at all, I can essentially run them all at the same time instead of sequentially, right? So I can get huge latency savings there. Uh-oh, I went back. And what's the last one? This is slightly lesser, but it also means I can batch independent fetches that go to the same place. So a lot of APIs, for example, Memcache has a multi-get, right? You can affect, if you need to fetch 20 keys from Memcache, you can actually fetch all 20 at once instead of fetching them 20 individual requests. You'll end up saving on like sort of traveling down into the network and back up and all that overhead, right? So this ends up being much faster. And so again, really, really simple example. Let's come like out of the clouds here. I want to intersect the friends of X and the friends of Y. This is like, you could imagine in any rule engine that you would ever write, this expression would appear, right? If you wanted to determine if something is likely to be spammy or whatever else. In every language, just about that there is, the friends of X and the friends of Y in a naive implementation is going to do 2 data fetches, right? That's 2 select statements to some database, so, one after the other. And it's unnecessary, right? There's no reason that those can't go together in practice, right? Since I know that the friends of function won't change anything, right? So I could, in principle, do those fetches together. A worse version of this problem is known as n+1 selects. Anyone who's ever dealt with object relational modeling will know this problem. It's sort of like you fetch some list from your database, and then you map a data fetching function over that list. If you do this naively, you're going to do n+1 requests. You're just going to sit there, whirring up your network stack and tearing it down n times, right? That's what you're going to mostly be doing in this. And this should only be 2 requests over the network. The first one gets you the friends, and then the second one is like a multi-fetch, right? You can sort of formulate the master SQL query to pull this off. And of course, when you have hundreds of thousands of lines of this stuff, oh, I did it again. When you have hundreds of thousands of lines, this stuff starts to get composed together, and there's and statements and huge piles of logic all get combined into this big, massive expression that has sort of data dependencies in it that you can't really easily expose, right? You have independent data fetches, you have dependent data fetches, and none of the languages that we would normally write these kinds of things in help you figure out what the independent data fetches are and what the dependent data fetches are. All right, so I won't abuse pure functions now. I want to show you how we solve this problem. I will start, let's go back. Look, it's a tree, okay? Imagine you have a program, a computation. We're going to go through this really quickly. It's organized as an abstract syntax tree, right? This is some computation you need to perform, right? You can travel both paths of every node in the AST until you hit a data fetch, right? And you say you can queue it. You say, okay, I'm gonna have some pending fetches. Basically, travel all paths. I should stop here to say that makes a lot of sense when we're talking about a tree. It makes a lot less sense when we're talking about your actual code, right? It's real hard to make the actual AST of your actual program do this, okay? And that's actually one of the things I want to talk about as we go forward. But anyway, the idea is simple, right? You go down here, you do as much as you can until you need to fetch data, and then you fetch it, right? And now that you have it, you pump it back into your AST, and it unblocks more of the computation. So all we're doing essentially is traveling the AST to find independent data fetches, do them all at once, unblock my tree, and proceed, right? Makes sense. I saw one nod. We do it again, so there's more fetches on the second round. You might get a cache hit, which is cool. Otherwise, you have a new data fetch to get, you pull that in, and then you finish, right? So this is the algorithm. This isn't sort of difficult in any way. As an aside, what's really cool about this data cache is if you save it, and you're really principled about only having a data cache and pure functions, everything that happens becomes replayable, right? So this is from the debugging and investigation perspective, this becomes a magical feature of a system. But the caveat here is you have to be principled about having actually pure functions and data fetches only, right? So you can't have random, or you need to know how to do pure random numbers. All right, onward. So solutions that work to actually write a rule language. You can build an interpreter, and in other words, you take your code and you actually make a tree out of it, a real tree in real memory. So that's like reification. That's what that word means. And you can traverse the tree just like I showed, like in memory, right? And that works. It's really, really slow. We should know that's how we've done it for 4 or 5 years. But why is it slow? Well, the add function is a node in a tree, and its child is 3, and the other child is 5. And you malloc a bunch of memory, and it's really should just be one machine instruction, right? That's really what it should be. Doing this natively in your favorite language is really hard. And this might be a controversial claim. Things like continuations and resumable computations, things like futures in your favorite language, they get you some of the way there, but not necessarily all the way there. And it actually becomes really tricky to actually solve this problem in your favorite language. I'm actually sort of proposing that as a challenge. So as I walk through how our solution of this works, if you think your favorite language can support it, please send me an email, please. By the way, is anybody from Twitter? Yeah, so apparently Twitter has a version of this that I've not seen. It's not open source, called Stitch. So they have something in Scala that can do something like this. I will describe a version of in Haskell. Okay, we're getting there. But if your favorite language can support this and you think so, let me know. That's a challenge, right, to the crowd. So I just said all this. Writing expressive code in your favorite language that executes in this sort of fashion is almost impossible. Now, you can write an interpreter in your favorite language, but actually making the code execute natively is almost impossible. Again, challenge. So again, what are my requirements? I want business logic, okay? I want business logic. This is business logic. I don't want like the programmer to manually pull out this and compose them in some way that makes the batching happen by hand, right? Because remember, this is part of some huge expression, right? And I want to do that optimization over the whole program, right? So this is the syntax I want. You can imagine in C++, I'm going to just kind of go through this in one slide, right? Like in a normal language, you say the friends of X returns a list of IDs. This is a naive friends of function, right? It's going to be synchronous. It's going to do a data fetch to get that list. It has to. That's the only way it can get that list. And so, oh, hey, I've been reading the C++ standard. They got this thing called futures. So I can sort of do this in C++. I can say like the friends of X is actually a future list of IDs. So at some point in the future, I'll have a list of IDs. That's great. That kind of works. But now how do you write intersect, okay? You can't take a list here because that means you actually need the list. And so that'll be like a false synchronization point because you don't have the list yet. So you might think like, oh, I'll take future lists in my intersect function. I challenge you to write this function, right? I challenge you to take a list you're going to have one eventually, take another list you're going to have eventually, intersect the two lists you don't have yet to return another list you'll have eventually. This is a fun function to try to write, and I've tried it. It's horrifying. I hope you like templates. All right, so I'm going to talk about Hackcyl. So Hackcyl is a Haskell-based DSL. It's basically meant to power rule engines. I will point out that everything we've said here is not only true of rule engines, it's kind of true of web servers. A web server basically fetches a lot of data and renders it. It's a reasonable assumption, though probably most non-trivial web apps don't do this. It's a reasonable assumption to assume that a web server doesn't have observable rights within the request. This sort of idea applies sort of widely, but in our case, it's really, really honed to be a rule engine, right? That's really that's sort of the language of our rules. That's the goal here. So the first and most important question is why Haskell? There's a lot of answers to this question, but we'll go back to sort of the most pragmatic, which is we couldn't make anything else work. So this Twitter project somewhere, I would love to see it, and I'd love to see, compare to see how it actually does what it does. I don't know Scala very well. Again, please send me some. I would love to see. I want to give you the sort of theoretical reason why this is hard, right? What you're really doing in this sort of approach is you need to hijack the order of execution of your abstract syntax tree in your code, right? You need to be able to stop a computation, return something, and then resume that thing later based on some application logic, namely that the data has been fetched. Most languages don't give you a way to do this, really, at all. More importantly, this part really screws you up. This is the intersect problem. Given two futures on the left-hand argument and the right-hand argument, how do you compose them into a new future on the way up? You don't have a good way to do this in almost any language. So in Haskell, applicative functor, okay? How many people know what an applicative functor is? Oh, nobody. Oh, wait, I got one. Yeah, so I'm not going to cover, these are terms that come from category theory. If you know anything about Haskell, everything comes from category theory. It's a programming pattern. But what it really does let you do is essentially examine both sides of it essentially lets you hijack function application, literally, like how a function gets called. And that lets you look at all the parameters of the function and do the kind of introspection that I want. It lets me hijack the fabric of the way we traverse the AST. Furthermore, there's a second problem, which is even if you solve that problem, you have a new problem, which is through this entire process, through this fabric, through the hijacking of the way we execute the AST, I need to thread the state of the pending fetches. Because as I'm doing all this, I'm enqueuing data fetches to be fetched, right? That's what I'm doing. Nobody wants to write an intersect function where the third argument is the list of pending fetches, right? That you have to manually compose. That's horrifying for a rule engine. So if I have to thread state elegantly through a computation in Haskell, well, how do I do it? Monads, that's right. So the word has made an appearance. I'm not going to talk about monads, but the point though is it lets you solve this problem relatively elegantly, which is behind the scenes, there is a piece of state that's floating along that it can automatically append and merge pending fetches together as we go up the AST. Okay, everyone, now I see confused looks. That's good. So anyway, summarizing, Haskell makes this possible. And that's a good enough reason for me, because everything else wouldn't work. The monads and the applicative exist in the guts, right? So it exists in the Hackcyl library itself. But from the user's perspective, it doesn't exist, okay? The user can basically write the trivial rules that we sort of saw before, right? And as I said, I'm going to keep repeating this because I'm going to try to con someone into writing the C++ version. This is going to be hard to do in your favorite language. So to give you an idea of what Hackcyl looks like, this is a Haskell function declaration. Okay, it's the account age function in Haskell. This is the naive version. It says, give you an ID and it returns some time or whatever else, whatever data type you want for how old the account is, right? This would do a synchronous fetch. This is very similar to what we saw earlier in the C++ version. The Hackcyl version looks like this, right? You return a Hackcyl time. And a Hackcyl can be thought of as a future. So this doesn't return a time. It returns of a computation that when you run it, will give you the time. Yeah, it's going to get meta. All right. So this works, right? So now I'm going to do the totally absurd thing, and I'm going to show a room full of people, only which like 20% of you know Haskell. I'm going to actually show you the Hackcyl internals in 3 slides. I'm going to try to explain them. You're not going to understand it, probably, but I think you'll get enough of it to understand how this actually comes together in practice. So like the actual interesting bits aren't the hard bits, so to speak. So in the beginning, you have a computation that's resumable, right? That's sort of the heart of this problem. And the computation produces a result of type A, right? So the result is an int eventually. It'll eventually be an int. The computation is in one of 2 states, right? It's either done with an A. By the way, this is valid Haskell syntax. It's done with an A. So if it's done, I've gotten the value. I'm finished, essentially. Or it's blocked. It's blocked on a list of pending fetches and the continuation to call once I have those fetches. Okay? So Hackcyl computation is a series of continuations. You run the first one, it will give you a list of fetches, do them, then run the continuation, and this process repeats until you get to done. Okay? So effectively, it's a stack of the rounds of data fetching. That's how this thing gets composed together. This is the main loop of Haskell. This is real run Hackcyl code with monadic do and everything. But it's actually really simple. In the beginning, you give it a Hackcyl computation to run. You give it a rule to run, okay? It runs it until it blocks. It's this line of code. It inspects it. It says, are you done? And if it's done, I return the answer, right? Not hard. If it's not done, I'm blocked with a set of blocked requests, fetch them, and then run the continuation, right? So this is the algorithm in Haskell that we described earlier, right? This is the algorithm with the tree and everything, but it's been built up with continuations in Haskell. So this covers almost everything. The only part that I haven't really covered is how you do the part you can't really do in C++, which is composing futures together, okay? And so this is done with the applicative, what did I call, wait. Yes, I'm sorry, applicative functor. And I'm not gonna show you the whole applicative functor, but I'm gonna show you its heart, okay? I'm gonna show you just the center of it. And this is where I'm gonna blind you if you've never seen Haskell before. So basically we start with a case statement. What is the status of the left branch of my computation? What is the status of the right branch of the computation? Unpack those two. If they're both done, then I'm done, right? And I propagate upward, right? Makes sense. If the right side is blocked on some computation, then I am also blocked with the same fetches, right? So the right side is blocked on this fetch or set of fetches. I'm also blocked on this set of fetches. And then I can create a continuation to run that is the composition of these things to be run in the future. Run in the future, right? Similarly, if the left side is blocked and the right side is done, I'm also blocked on this time the left side's pending fetches. And I do a similar composition here, you know, go read the Haskell book if you want to see how this works. But then finally, the interesting bit, right, is if both sides are blocked on separate sets of data fetches, I myself am also blocked, but I am blocked on the combination of the two, right? And so essentially at every branch point in the AST, this code happens without the client knowing about it. The client isn't composing all these futures together. Haskell's doing it as it's tearing apart and rebuilding the AST, right? That's basically the solution to the problem. So anyway, go back to our sort of naive example, right? Like this is a totally fake rule that combines a bunch of the things we've seen before, right? What, you know, how many friends do I have? You know, are the number of common friends less than 5? And if the average account age is less than 10, then something shady is happening, sure, right? Why not? And here's some helper functions to get us there. Here's the Hackcyl version of this exact rule. Right? Did you see it? Who saw it? All right, so here we go. So this version, okay, not the other one. This version is the naive version. This is going to do a data fetch here. It's going to do a data fetch here. It's going to do data fetch here. This doesn't return a Boolean. This returns a Hackcyl Boolean. This returns a computation that when run will generate a Boolean eventually, right? And so this doesn't do one or n crazy data fetches. It essentially finds all independent data fetches, does them all together, and iterates and unblocks the ST and travels down the path, right? So that's the heart of the beast, right? This is way more efficient than the previous slide, even though they're like, the same code, right? That's the idea. So all right, so let's talk about actually using it, right? Our rule engine is a Thrift service, so all of Facebook, all of Instagram talk to this thing over Thrift, right? And that's the basic way you can do this thing with RPC. We have like sort of update mechanisms so that we can update the rules on the fly. But that's sort of the input. The more difficult, Facebook and Instagram, I said that. The more sort of, I shouldn't say difficult, the more work you have to do is actually teach Hackcyl to talk to all your data sources. The abstraction for talking to data sources is really easy. It basically says, I give you a batch to go fetch, do it as efficiently as you can. And sometimes you can't do it very efficiently, sometimes you can do it really efficiently. And that's a really good, basically Hackcyl's taking care of batching everything up for you, and then you have to go ahead and actually get the thing. So for us, there's other Thrift services, right? We just talked to all the other Thrift services within Facebook. We talk to Memcache, where we can use the multi-get APIs. And we talk to Tau, which is our graph API. I can say get the friends of X is actually a fetch to something called Tau, which just feels like a graph database, right? All right, so okay. Here's the part where I let off the functional programming gas and I sort of zoom it all back out for you. Remember the goal here. The goal was to build a rule engine that was latency sensitive, that could execute our business logic and keep the latency as tight as possible so that we could, for example, log you in 100 milliseconds instead of 40 seconds because of pathological I/O behavior, right? This powers all of Facebook and Instagram, and it's been crazy wildly successful, right? Part of the reason that this has been so successful and we've invested so much in it is because we have so much code that fits this pattern. We have so many things that say, oh, this looks kind of sketchy, flag this, or oh, this looks kind of crazy. We can even use it for just normal rules, right? Like that you want to update on the fly. Like how do you route, through the different mobile carriers, a text message or a push notification, right? Like how do you notify a user through their favorite method and navigate all the different intricacies? And it ends up being this big, gross, giant pile of if statements, and it runs beautifully in a system like this. Okay, so I'm done. This is open source, by the way. If you want to play with it, it exists. It's Haskell, so you have fun. Does anybody have any questions for me?
Are the rules dynamically generated, or do people have to code them up by hand?
Most rules are written by hand.
Okay.
So it doesn't have to be, of course. There are places that we do sort of dynamically generate rules, and obviously there's machine learning and all this, so that's in some sense a dynamically generated rule. But yeah, most rules are written by hand. It ends up being just simple rules.
Can you comment on what informs the lifetime of a rule?
Yeah, rules are permanent. So it's an updatable code base, and essentially when you change something, it goes out, in other words. And we don't right now have the ability to sort of say, oh, this is banned for the next 2 hours, or this is banned for the next month. There has been talk of actually implementing. I mean, it wouldn't be very hard to sort of have them horizon eventually, but at this point, we've not done that. We've not found the need. So it's not a terrible feature. I mean, it's probably a good feature to have. Anyone else?
Hello.
Yes.
When we batch things for fetching, we consider different sources. Like Memcache might be faster than other sources, and consider them differently.
Yeah. So not automatically. So the framework is cognizant of different sources. So in other words, it'll get all the independent data fetches sort of by data source and call to each data source at the same time, so they all overlap. You could, in the Haskell code, of course, route to the right data source based on some additional business logic if you want. But our code basically just when you make the friends of function, you call into the data source that gets you the friends of. So we don't have any built-in notion of automatically routing. But obviously you can. And we end up building client code that, for example, uses memcache. So you can put memcache in front of something, and that just ends up being client code. It just ends up being normal Hackcyl code that is an abstraction. It's a function that you would call. Yes.
Can you say something about how you incorporate machine learning into the rules? So,
Yes.
so you train the model offline, and then what?
Yeah. Well, at a very high level, our rule engine not only gives you the ability to have policies, but also essentially any top level name can be logged. So in other words, if I say x equals and a huge expression, I can actually write x to a log. And then what that allows me to do is take that log of all these named features, join it on some external data, for example, mark as spam labeling, and then generate a machine learning classifier using Hackcyl as the feature definitions. So the Hackcyl rules essentially can also be used as features in a feature vector for machine learning. And we actually have a whole pipeline for training models in that way. So one of the ways people train models is they use Hackcyl to define about 100 different features or whatever. They take some amount of data, they run our machine learning infra on it. Is this model going to work? Random forest, et cetera, et cetera. And if it does, then we can ship it. And one of the functions in Hackcyl is to sort of call this classifier. And we have an infrastructure for essentially training, pushing, and then evaluating machine learning models. Yes.
You said all the rules execute in any order. There's no sequence, right? So let's say you have like 10, 20 rules. Suddenly you wanted to push a rule that's very high priority. So how do you handle that situation?
This is an interesting question. As of today, we essentially have a timeout, and it's all or nothing. So there's actually a trade-off between, do you want to execute everything as fast as possible, or do you want to get as much partial results as you can in a time limit? And you can't win both of those fights. You have to pick one. So we've optimized our system to get all of the answers as soon as possible. But if there is a bad policy in there that takes 6 months, every request is going to time out. And we basically, we have a whole lot of infrastructure and tooling. This is where the ability to replay becomes really handy. Suddenly, everything's timing out. Why is it timing out? You can do analysis very easily once you have the data caches. And then you can say, oh, here, this policy's bad. Let's go fix it. And so we end up manually monitoring and fixing a lot of this stuff. But you could do it the other way. You could order them and actually prioritize and actually say, I have 100 milliseconds. Let me get as much answer as I can on this list before I run out of time. Yes?
Can you comment on how the launch of the system for Instagram affected the price of Instagram followers?
So he asked me if I can comment on getting this onto Instagram affected the price of Instagram followers. I do not know the answer for certain. Certain enough to put it on YouTube. This is going on YouTube, right? So I don't know the answer to that. Did anybody back there know the answer? Yeah. So I can tell you from like the Instagram founders who I've spoken with about all this, I know that they are incredibly pleased with the effect on the short term of spam on Instagram. It was like we did a lot of damage really, really quickly because amazing amounts of stuff got surfaced instantaneously through all the tools we'd built, and we just started like it was like a machete right through the jungle, so to speak. But I don't have quantitative numbers, not that I could give you. I know it was good, though, for our definition of good.
So I think I miscommunicated the last question.
Oh.
So when I said like high priority rules, like I want some rule to override the results of all other rules.
Yeah. So okay. So that can be built in the language. We actually have that abstraction in the language where you can list your rules in like a waterfall mechanism. The problem is you end up creating like a false serialization if you do it in this sort of naive way. So we haven't actually run into the case where it's super, super latency critical and we want that kind of serialization. One of the other things we do is we run all the rules and we give you back all the results. Like we don't like, what's the word? We don't mediate. So if if one rule says like promote this person and one rule says fire this person, that's sort of on you as the caller. So if you have a built-in priority, you can sort of rank them on your side and sort of figure out how to mediate what you want. But yeah, there's different approaches there. But so by default, what we do is we run everything together, and you can introduce serialization if you want using like if and other sort of obviously higher level like Haskell sort of if-like conditionals. Question in the back.
So you mentioned the timing out and looking at the rules that were taking too long. How does this system affect your asynchronous results as well? How does that fit in?
Yeah, so the asynchronous system and our system are essentially the same system. In fact, all the requests come to the same place. It's just a question of will this time out eventually or not? And that's actually arguably not the best architecture decision because optimizing for throughput isn't the same as optimizing for latency. But I'm not sure that quite answers your question. When a timeout occurs, essentially, the client knows that it can do what they want. On average, what we typically do is it closes, it fails safe. So the event can happen. And we basically depend on asynchronous stuff to clean it up. And it absolutely has occurred that the growth team sees a huge spike in crazy engagement numbers. And it turns out that all of the growth that happened on day X was from 3 weeks earlier when our system was timing out for 4 hours. They made all their horrible accounts in a 1 4-hour period and then turned them on in 3 weeks. And so that does happen. And so we do have sort of asynchronous jobs that catch a lot of this stuff often. It's probably not as good as it could be in terms of, a timeout happened. Maybe I should run an extra set of checks on the asynchronous side. But that's the answer.
Do you guys use any of these tools to look at historical data?
Yeah.
Say, we did this 4 years ago, but we don't ever know what happened. Can we apply the new tools we have against this data?
Yeah, so there's no reason that you can't take a log and pump it through the system just like you could, actual live traffic. And we have that system that essentially lets you generate jobs and, take a log and pump it through. So we do. And then we also have, I didn't really talk too much about this, all these aggregation systems that deal with reputation. So you can essentially re-look at something else that happened with today's reputation information. Because a lot of times, the first time you see something evil that has no reputation, it becomes evil later, and you need to kind of go back and take today's reputation information and apply it retroactively. So we do that. It's part of our async pipeline.
Do you have any logic for catching and throwing errors? Did you get enough reputation data to fail open or to fail closed?
I missed the question. Catch who?
So if you're if for whatever reason it just fails, you catch an error and you have to throw a response, do you have any logic behind saying, I've built enough in this query to make a decision at that point?
No, we
or
don't.
Or do you just fail close or fail open?
So yes, the answer to your question is we do not today. If I see a timeout coming, can I salvage it and get an answer back based on whatever partial information I have up to this point? Right now, the system does not do that. It could, but it's not. It's, as I said, it's really built. It'd be interesting to see how often, if you were to hypothetically stop it and say, how much information do I have now? How much do you actually have? If that would be of any value. It's something we probably could do, but today we don't. I mean, literally, if a timeout happens, it's as if nothing happened, and for better or worse. That's the way it works. We basically try to keep the timeouts. So in spam fighting, you keep the timeouts. If 99.9% of everything gets through, meaning successfully classified, that will cut the most viral attack in the world will have a viral coefficient below 1. If you can clean out 99.9% of it, it can't spread, essentially. So that's great for spam. That's not as good for is my internal network compromised, right? For example, because you really don't, you want more than 3 nines on a system like that. But for spam, that's often where the bar is. It's essentially, it's like the Purell. If I can get 99.9% of the bacteria, it can't spread, and that's good enough. So that's sort of the high level design decision that have been driving a lot of these types of decisions.
So there's a really cool project, crazy project called Captain Proto, which features something called a time traveling RPC, where you can use the result of a previous request and a future batch of requests. How have you talk about have you had to modify backend services for servicing batch requests specifically?
Okay. Yes. In fact, we frequently go to people and say, I need a batch API for your thingamabobler. And in Thrift, this tends to be relatively simple. You can just add a new Thrift function that takes a vector of all the other parameters and returns a vector of responses. And that's typically how we do it. So I'm not super familiar with Captain Proto's, that part of it at least. So I don't actually know. But yeah, I mean, we do. We all the time. We say, I need a multi-get version of this because I don't want to, pay the network stack n times to fetch n data.
We have time for one more question, if we have one more question.
I'm sorry about the monads.
And
Let's
so,
go.
since we have no more questions, well, you have the opportunity to talk to Luis. Thank you very much. And I also wanted to tell you.